Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is redundant connection. So let's go to LeetCode. In this problem, a tree is an undirected graph that is connected and has no cycles. Basically, that's a fact. The tree is an undirected graph and it doesn't have any cycle. Otherwise, it's a graph, right? You are given a graph that started as a tree with n nodes. So given that our nodes are labeled from 1 to n, with one additional edge. So there is an edge that has been added to this connected undirected graph, which means we are introducing a cycle. So the added edge has two different vertices chosen from 1 to n and was not an edge that already existed. So the graph is represented as an array, basically these edges of length n, where edges at ith position is a pair a and b, where it represents like there is a connection between a and b. So there is an edge going from a to b and b to a because it's undirected, so you can say that's like going from both ways. So now indicate that there is an edge between node a and b. I mean, that's we have understood. Now return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs basically last in the input. Okay, so let's go over our example 2 because that's a better example to understand our solution. So here we will be given n nodes and we will be given n edges. And if you remember from the graph theory, like to have a connected component of graph nodes, basically if there are n number of nodes, you only need n minus 1 number of edges in a undirected graph. Well, in this one, we will be given n nodes and n edges. That means there is an extra edge. That is exactly what we will be returning as an answer. Now, if you see right here, if you see in this component, we are given 5 edges, and even if one of these edges, if we remove, we will still have a connected component. So let's say this is the edge we get rid of, then you can see that our graph will still be a connected graph through this line I just represented. If you basically get rid of this line, then we can still have this connected graph in this way. And similarly, we can remove these two edges and there will still be, our graph will still be connected. So now how do we find out that extra edge? Well, there is a famous algorithm that's called union and find, but I'm not gonna introduce it right away. Like I'll make a separate video. I'll upload that algorithm. It's really important. It has these two little cute functions, union and find, and then you basically create the graph at the same time you are visiting the nodes. But we will be doing the same thing here using DFS. We will be doing the same thing, and then we'll be finding if these two edges, we will be using these. We will be using edges. We'll go edges by edges and then create our graph, just like how we create our adjacency list and then we traverse our graph. We have been doing it in a lot of problems. So at this point, I think you'll be comfortable enough creating that adjacency list using these edges and then visiting the graph. But in this one, it will be just a little different. We will create that graph adjacency list, but while we go through these edges, we will check if we have already visited these these nodes. And let's actually dive deep into the try run. So what I'll do is I'll create graph. Let me just move it right here, and I'll create graph adjacency list. So I'll have this as a dictionary. And then I'll have my DFS function. So here we'll have our DFS. Okay, so what we'll do is we'll go edge by edge. So in this case, let's choose our first edge, which represents a connection between 1 and 2. So this is the connection it represents, 1 and 2. So there is a connection between 1 and 2. Now I have to create these two nodes and then I have to basically append it to each other's neighbors. But before I do that, I have to also have visit set to mark things visited so that I'm not basically again trying to visit them. But if they have already been visited, that means they are already part of the connected component, and I do not need to introduce, I do not need to create that edge, and that is the extra edge that I'm just introducing, and that's the one I will be returning as an answer. So what I'll do is, I'll use a for loop to basically go over all these edges, and when I find these two, this pair of this edge that has already been visited, and if I run my DFS on it, that returns true. That means it's already like basically you could reach v from u. U is the source vertex, v is the destination vertex. That's how, you know, in graph theory, like we have studied things. So we'll have this visited set. We'll have this visited set. I just want to write it in green. Visited set. Okay. So first we're gonna go over our first edge is. And if we say like v and u and v, sorry, my bad, v and u and v, so our first u and v is 1 and 2, and now let's check, are these two in my visit set? Well, they're not. So what do? We are going to run DFS on it. Okay, well, okay, not right now. First, let's check if they are in my visit set. If they are not, then let's add it to the graph. I will run the DFS on my graph, right? So what I'll do is I'll just add them to my graph. So here to my graph, what I'll do is like I'll create 1 and 2 as these two keys, and then in these two lists we'll be adding their neighbors. So 1 has 2 as neighbors and 2 has 1 as its neighbors. All right, then what I'm gonna do is I'm gonna go to the next edge, 2 and 3. Well, is 2 in my visited? Well, yes. 2, no, actually no, 2 is not in my visited yet, but I know it's in my graph. But it's not in my visited. So what I'll do is I will check, is 1 in my graph? Yes, 1 is in my graph, 2 is in my graph, but is 3 in my graph? No. So what I'll do is I will again add 3 to 2's neighbor and 2 to 3's neighbor. Okay, then I go to the next edge, and then I'll basically check if 3 is in my graph. Yes, it is. Is 4 in my graph? No. So I'll add 4 to 3's neighbor, and then 4 will have 3 as its neighbor. Then what I'll do is go to the next edge, then 1 and 4. Is 1 in my graph? Yes, it is. Is 4 in my graph? Yes, it is. Now, u and v, source and destination, they're both in my graph. Now let's run DFS to check if we can reach this destination. So right now, this is the first edge that has both its vertex in my graph. That means now so far the graph that I've created, can I visit 4 from 1 using DFS? If I can, that means this edge that I just came across, it's an extra edge. Okay, so if u is 1 and v is 4, so I'll have my DFS. So I'll call it DFS, which will be taking source and destination, and then it will also we can send visited set or like graph, but we don't have to. Like we'll be writing this as an inner function, so we'll have access to it. Okay, so we'll have access to it, source and destination. Now if the base case would be DFS is a recursive function, so if DFS, you can see nicely. Okay, so if source is equals to destination, then we can return true. Now what we want to do is from this source, I am going to explore all its neighbors. So for, we can say, neighbor of graph of source. Okay, I'm going to explore all its neighbors. So if DFS basically returns true on neighbor of source, that means we were able to get to this base case, and we just return true. So we can return true from here as well. return true. Otherwise, we couldn't find a destination while traversing using basically traversing the graph using source, and then we can just return false in the end. That means we are done doing our DFS and we will return false. I just wrote false, but like you can say return, okay, return false. So that will be it. That will be it. So what will happen is when we found 1 and 4 in my edges, then I will call DFS. And remember, we will make use of our visit set because it's an undirected graph. So here I will add these neighbors to my visit set, or maybe this is the best place to add these, visited.add this src, okay, and I will only call this neighbor if I'm not if that neighbor is not in my visited set. Okay, that I think that was the part I was missing, like there was in my head like I'm missing something. Yeah, I didn't use visited, so visited will be used over here. So if neighbor is not in visited and this returns true, then you can return true. Okay, so if it is not in visited, then you can call DFS on it. Otherwise there is no need of calling DFS on it. Either we must have returned true, or we couldn't reach there. All right, so let's write the solution. All right, so let's write our solution. First thing, we will need a graph. So this time let's just use default dict, which will store list. Then we are going to basically go over all the edges. So let's call it V and U, source and destination in my edges. And now I can check if let's say if U in graph and V in graph, V is also in graph, and DFS also returns true on this one. So U V also returns true, then I can just return that as my answer. So U and V, right? Otherwise, and we will write the code for DFS. We'll write it here. We can write DFS. Let's write source and destination. We can call it test, and then let's have the visited set created as well. Otherwise, at this place, like if they don't exist in our graph, that means we have to add these to our graph first. U will be added to V will be added to U's neighbor. So append V, and the same thing is done. U will be added to V's neighbors. So we will have U as its neighbor. Well, in undirected graph, that's how you do this. Let's write our DFS now. So as we discussed, if source, we are trying to, if these two are in as part of my graph, now I'm trying to check, are they connected? Can you is this edge necessary? Like, are they already connected? Which I think if we have already added them, then you should be able to visit them. All right, but we are using DFS to confirm that, can you reach the source and destination if they exist in our graph? Like, they might not be connected, and you might need that edge. And the reason is because these U and V that are being introduced to you could be just disconnected component. Although we have been given that it's an entire connected component, and there is just one edge that's creating the cycle. So I guess there is a lot of things to learn from this problem about graph theory. So if this source is equals to destination, then we can return true, and that means we could reach destination from source. And here we will return this an answer because we don't need this edge, because those two vertices are already part of graph and they are reachable from each other or from source to destination. Otherwise, what I can do is I'll add this to visited. So visited dot add, and I will add source because I have visited it. And then for neighbors in my graph, in my graph of source, I'm trying to visit all those neighbors. So if this neighbor not in visited, so if it is not in my visited set, and also if DFS, if I run DFS on this neighbor and it returned true to me, which it might, because I'm trying to reach destination through neighbors and their neighbors and their neighbors, you know how DFS run, you know it very well, I will return true. All right, otherwise what will happen is like I will explored all this connected graph, and then I could not reach destination through source, and given that destination and source, they are part of my graph, and I still could not reach it, that means I needed that edge, you know, I needed that edge. So I will just return false from here, and everything else will be taken care of right here. So that will be the entire code. That will be the entire code. We are given, it's guaranteed that there will be an extra edge, because to connect the entire graph you just need n-1 number of edges if you're given n number of nodes, but in this one we are given like, you know, that extra edge. So one more thing that I've realized is this visited set, we are running basically this DFS on these edges, like these two nodes that are part of graph, but when we run DFS, we are running a fresh DFS. So this visited set needs to be reset each time you come across these, you know, these two edges which are part of graph, and you are gonna run basically this DFS on it. So I guess like we need to send this as a parameter also. So now I think that will be a better way. So we needed to reset this. And I think that this is the place like to put the visited set and reset it each time you are trying to visit these edges. So now let's zoom out and try to run these. I will zoom out. I've already zoomed out, right? So now you can see that our code is running. Let's try to submit it. Awesome. It's not like super efficient. It's not super efficient. I think there are better solutions using union and find. They are much more efficient. But like I guess this is it for now. Once we learn union and find, then we will do it again. I'm just trying to find. Yeah, it will be somewhere around like 1920. So okay. So time complexity for you are visiting all these edges or nodes, but for each node you are running this DFS, which also takes the same amount of time, v plus c. So worst case it would be you know n into n, which makes it n square time complexity. And for space complexity we will be at v plus e. We are storing the entire graph in our you know, graph adjacency list. So that will be it. By the way, this could be v square or like n plus e. I know, like I know, you know, I tried, you tried, we tried, whatever. All right, so now let's go back to AlgoYogi, mark this problem solved, and I think we will be solving it again using union and find. So please find later. Anyway, see you guys later in the next video.